Let's solve again more problems for the remaining conic sections, but this time in other real-life applications, for you to be familiar with different situations that you may encounter in solving word problems involving conic sections. Okay, but before that, are you familiar with this place? Do you know that this is the longest elliptical shaped tunnel here in the Philippines? Okay, so Kaibang Tunnel is a hole first under Mount Pico de Loro, connecting towns of Ternate, Cavite and Nasugbu, Batangas. Locals from nearby towns flock to this place to enjoy the cold weather and the beautiful scenery. So having said that, now move on to our next problem. Kaibang Tunnel, the Philippines' longest subterranean road tunnel, has the shape of a semi-ellipse and with a vertical clearance of about 16 feet. What must be its height at the center for a passing track 12 feet wide to be able to fit through the tunnel? Round off your answer to the whole number. So we have this word semi-ellipse. So that means we will be using the concepts that is involved with ellipse in order to solve this word problem. So our tunnel here must be in the shape of half of an horizontal ellipse, with half of the base longer than its height at the center, because that is only the possible shape of a semi-elliptic tunnel in real life. We also have this term, vertical clearance. So if you don't know the meaning of vertical clearance, it is the unobstructed vertical height inside the tunnel. So it was mentioned that this measures about 16 feet. But in reality, it's actually 4.85 meters or 15.91 feet to be more accurate, according to an article about this famous tunnel in the Philippines. So now, from the question, the problem is asking for the height of the tunnel at the center. If there will pass a track that is going to fit the tunnel. So let's say, of course, a track is commonly rectangular in shape. So again, if you will try to visualize this situation, this will look like a semi-ellipse with the largest rectangle inscribed in it. So to visualize it, it is better if you will be able to illustrate it on the Cartesian plane so that we can identify certain points based on the values given for us to find what's being asked in the problem. So if we will simply illustrate it, it will be like this one. So as you can see in the figure, we have placed the center of the ellipse on the origin. So again, it is advisable if you will maximize the use of the origin in illustrating the conic section involved in a situational problem, so that we can solve it easier and faster. So its base will be on the x-axis. So it was assumed that it is 36 feet across. So we will be having 18 feet on both sides. So we can say that A is 18 because the whole major axis is 36 feet. So we don't know the value of the height at the center. So we let this line segment right here be B. Which represents the length of the semi-minor axis in an ellipse. So therefore, we will be using the standard form of the equation of a horizontal ellipse. So we have x minus h squared all over a squared plus y minus k squared all over b squared equals to 1. We know that the center is at 0, 0. A is 18 and b unknown. Therefore, we have x squared all over 18 squared plus y squared all over b squared, which is unknown. Is equals to 1. Simplifying this, we have x squared all over 18 squared is 324 plus y squared all over b squared is equals to 1. So this is now the equation that represents the tunnel. If we will continue this is a full ellipse. So let's say this rectangle, this blue one right here, represents the track. If you will inscribe it in a semi-ellipse, it will be like this one. So we know that this passing track, which fits through the tunnel, should be 12 feet wide. So the semi-minor axis of the ellipse divides it into 2. So we have 6 feet on each side. So to maximize the height of the track, it should be the same as the vertical clearance of the tunnel. So the corners of the track, as shown in the figure, would have to just touch the ellipse. So referring to our figure, the point 616 is also on the ellipse. So it should fit the equation. So plugging in, we have squared all over 324 plus 16 squared all over b squared equals to 1. So we need to find the value of b. The simplifying, we have b is equals to the square root of 16 squared all over 1 minus 6 squared over 324. So calculating this, we have b is equals to 12 the square root of 2, or it is approximately equal to 16.97. So from the problem, we need to round off our answer to the whole number. So this is also approximately equal to 17 feet. So must be in feet. So this should be the height of the semi-elliptic tunnel at the center. Okay, let's move on to the last example of situational problems involving conics. Long-distance radio navigation for aircraft and ships uses synchronized pulses transmitted by widely separated transmitting stations. These pulses travel at the speed of light, or 186,000 miles per second. The difference in the times of arrival of these pulses at an aircraft or ship is constant on a hyperbola having the transmitting stations as positive. Assume that two stations 300 miles apart are positioned on a rectangular coordinate system at points with coordinates negative 150, 0 and 150, 0, and that a ship is traveling on a path with coordinates x, 75, as shown in the figure. Find the x coordinate of the position of the ship if the time difference between the pulses from the transmitting stations is 1000 microseconds, or 0.001 second. So we have here an interesting and important application of the hyperbola, the long-distance radio navigation, commonly known as the LoRa, or long-range navigation. So it uses the principle of the hyperbola to locate the position of a ship or an airplane. So it is known to lie on a hyperbola, with the transmitting stations that are in fixed position as the foci, which send out signals at the speed of light. So looking at the GIF, we can visualize that the route of the ship from the problem is the same as one of the branch of a hyperbola, since it follows the path where it experiences the same time difference or the path where the difference of its distances from two stations is kept constant. So, obviously, in this word problem, we are referring to hyperbolas. So again, we are going to use the concepts that we know about hyperbola to solve this word problem. So, as you can see from the figure, the hyperbola formed by tracing the path of the ship is illustrated by placing it in a rectangular coordinate system, with the center of the hyperbola located at the origin, which is the point midway between the two stations, 300 miles apart. That's why the coordinates of the stations are given negative 150, 0, and 150, 0, as stated in the problem. Since the line connecting these fixed stations, which represents the transverse axis of the hyperbola, is also placed on the x-axis. So looking at this illustration, let's say the path of the radio signals transmitted by the two stations in fixed position is these broken lines. So it was mentioned in the problem that the times when it received the pulses transmitted by each station differ by a certain constant, with absolute value around the difference so that it is always positive. So the locations or instantaneous positions that the time differences experienced by the ship are always equal to a constant value, then its path as it navigates at the sea. So that's why, if you will recall the definition of hyperbola, that this path, which is then a curved line, is in fact one of the branches of a hyperbola. And in this figure, it is on the right. Now, in this problem, our task is to find the x-coordinate of the position of the ship from the figure at x75. So with that, we have to use the formula or equation for horizontal hyperbola, since the transverse axis of the hyperbola is also the x-axis. So we have x minus h squared all over a squared minus y minus k squared all over b squared is equals to 1. Now, it is centered at the origin. So that means we will be using x squared all over a squared minus y squared all over b squared is equals to 1. Again, we use this formula because the transverse axis of the hyperbola is horizontal. So we need to find the values for a and b. Now, Now, it was mentioned from the problem that the time difference has a constant value of 1000 microseconds or 0.001 second. Since the difference between times of arrival of the pulses at the ship is constant, multiplying it with the constant rate or speed of the travel of these pulses will give us also the constant difference of distances from the ship in every locations to each transmitting station. So it was also given in the problem that this rate is equal to the speed of light or 186,000 miles per second. Therefore, if we let this be d sub 1 and this one also be d sub 2, then absolute value of d sub 1 minus d sub 2 is equals to the product of 0.001 second times 186,000 miles per second. Absolute value because, recalling the definition of hyperbola, our only concern here is the magnitude of the constant difference. But since the point or location of the ship is on the right, then we can rewrite this at d sub 1 minus d sub 2. Since d sub 1 is always greater than d sub 2 here, so it is equals to multiplying the units second will be cancelled. So it is equals to 186 miles. Recall that this constant difference is 2a. So equating, we have a is equal to 93. From the figure, recalling the concepts of hyperbola, RC here, which represents the distance of either one of the foci to the center, is equals to 150. Or R2C here, so your distance between the foci is equals to B100. Therefore, C is really 150. Now we can find the value of B from C squared is equals to A squared plus B squared. So we have B is equals to the square root of 150 squared minus 93 squared. So it is equals to the square root of 2,000. Again, our goal here is to find the equation of the hyperbola. So from the values that we found, we have x squared all over 93 squared minus y squared all over 13851 is equals to 1. So simplifying, the equation is x squared all over 8,649 minus y squared all over 13851 is equals to 1. Now, after that, we have to identify what will be the value of x given that y is 75. Again, this point right here, which is x 75, is part of the hyperbola. So we can use this equation to identify the value of x. So y is 75. We have to know what is the value of x. So now let's substitute. So x squared, we don't know that, over 8,649 minus 75 squared over 1,3851 is equals to 1. So solving for x, we have the square root of 8,649 times 1 plus 75 squared over 13,851. So we have the estimated value for that. So x is approximately equal to 110.28. So we have now the x coordinate of the position of the ship.